Hello, I'm Sid Ulrich, and today I'm going to be discussing my recent project involving SuperDARN electron density data. My project was to investigate the quality of an existing method of determining F-region electron densities from SuperDARN elevation angles. SuperDARN sends high-frequency radio waves into the ionosphere and measures the backscatter, or echoes. The main source of echoes for SuperDARN is field-aligned irregularities. Because of this, we get echoes when our radio waves are propagating perpendicular to Earth's magnetic field. Now, the propagation of these radio waves is dependent on how they are refracted traveling through the ionosphere. In 2011, Dr. Ponomarenko proposed a method by which we could infer electron densities from these propagation conditions. The method starts by looking for echoes with constant elevations. As we see in this diagram, echoes traveling along the same path will all reflect from approximately the same height. And by looking for this constant elevation in SuperDARN echoes, we can determine the F-region peak density. How exactly? Well, we do it by using Snells Law to find the index of refraction. We know that our propagation is perpendicular to Earth's magnetic field, and we also know what elevation angle the radar is measuring. We can solve Snell's law to find the index of refraction in the ionosphere, and from that we can relate the critical frequency and ultimately the electron density. SuperDARN is able to determine the elevation at which echoes arrived by using interferometry. Most SuperDARN radars have an interferometry array located somewhere near the main array of antennas. By measuring the phase difference at signals received at these two locations, we can use trigonometry to determine what elevation the signals arrived from. However, because of the spacing of the interferometry arrays, most radars have a maximum measurable elevation angle because elevations beyond a certain height will lead to phases that are indistinguishable from a lower elevation. Ambiguity in elevation angles is one of two major problems with this method. The other being that under conditions of very low electron density, we do not have sufficient refraction of HF radio waves to reach that orthogonality condition, which means that we receive very few backscattered signals and very little data. The goal of my project was to assess the quality of this method by comparing its results to independent observations by other instruments. The Rankine Inlet SuperDARN radar is in a convenient location for this because its field of view overlaps with two other instruments, the Resolute Incoherent Scatter Radar RISER and the Canadian Advanced Digital Ionozone CADI, both of which are located at Resolute Bay. CADI has been measuring the ionosphere for many years. This ionozone transmits pulses of varying frequency into the ionosphere and measures the time that it takes for these signals to return. When CADI is transmitting signals at or above the critical frequency of plasma, these signals will not be reflected by the plasma but will instead go out to space. We can use this to find the critical frequency or the maximum critical frequency of plasma, which is associated with the F-region peak electron density. Our other instrument was the Resolute Incoherent Scatter Radar, which works quite differently from the other two instruments. It sends out a very high power radio signal that is a frequency much higher than the plasma critical frequency, because rather than trying to bounce a signal off of the plasma, it instead is looking to measure plasma thermal fluctuations, from which it can determine the plasma frequencies for ions and electrons separately. In this study, we are only concerned with the F-region peak electron density. So we take RISER's large number of measurements, and we fit a curve or just take the maximum density from any given measurement to construct our own dataset. Now unfortunately, at the time of data analysis, we had only about 60 days worth of RISER data for the year 2016. We can start by looking at the data for a single day. Here we have Rankine in blue, RISER in red, and CADI in green. It's hard to say exactly how well these instruments agree, although the trends definitely do seem to agree. One of the more definitive things we can say from this plot is that neither CADI nor Rankine make measurements when the electron density becomes very low. For example, during the dawn sector here. The point worth mentioning with this plot is that spot in the afternoon where riser shows an unusually low electron density for the time of day, and Caddy has no measurements. At this point, Rankine is showing rather high electron densities. We believe that this disagreement is explained at least in part by the fact that while riser has a very well-defined field of view, Rankine, especially with our method, will tend to always find the highest electron density within a beam. Since SuperDARN beams are quite wide, we believe that this allowed it to see an electron density outside of riser's field of view. Finally, Rankine's density measurements are just lower than the other two instruments at night. We've done a direct comparison between the measurements made by the different instruments, Rankine versus Caddy here in green, and Rankine versus riser at the bottom in red. They show a general trend towards a positive correlation, although it definitely could be better. To make a better picture, we can look at more data. Here is a comparison between Rankine and Caddy during February of 2016. Now this plot is rather busy, it has a lot of data on it, so let's start simply by ignoring those pink points for a moment. I'll discuss them later. The tiny dots in black are the raw Rankine measured densities for every day in February. The blue squares are Rankine medians on a half-hour basis, while the green dots are similar observations for Caddy. As we can see, they show similar trends, both showing a slight increase in the morning, a decrease around 6 o'clock local time, followed by an increase in electron density towards noon, a decrease in the afternoon going into the night. Now, as I said before, Caddy has many years of data. So does Rankine. So we can get an even better view of just how these instruments agree or not by looking at many years of data. And so what we have here is some line plots showing the density from 2008 to 2018. Now, quite obviously, there's a large discrepancy in densities measured by Rankine versus those measured by Caddy in the nighttime sector here, where we see that Caddy has a very consistent pattern, in fact in all time sectors, of measuring high densities during the summer and low densities during the winter. We can also see over the course of many years here that there is a general increase in overall densities towards the solar cycle maximum 2013-2014. In most time sectors, Rankine does show the same trend of lower densities in the winter and higher densities during the summer. However, in the nighttime sector, there is the case where Rankine densities become very large at winter. We see that in the summer, especially during the peak of the solar cycle, that Rankine densities are consistently quite a bit lower than those measured by Caddy. Now in these plots there are red and blue lines. Now the red lines, well they're red now, these are made from taking all of the density measurements, which is why we prefer the blue lines. The blue lines disregard density measurements which had what we called a high phase. These are measurements where the radar's elevation angles are close to that ambiguity that I talked about earlier. By removing these high phase points, we can see that at least some of these apparent winter maxima among Rankine data are almost entirely removed, making Rankine's correlation with Caddy much better than it would have otherwise been. The removal of the high phase points also increases the correlation in other time sectors. However, it does not fix the low densities observed by Rankine during the summer. When densities are very low, we tend to get very few good measurements, and I'll go back so that we can look. Here in this morning sector, we see that the raw data, indicated in pink, deviates significantly from the data with the high phase points removed. And this is mostly because there is much less data overall, and so these few points with a high phase have a stronger effect on the data. Now we see that there are also a few high phase points, and these are all very obvious outliers, just on a single day. Beyond this point, I have removed all of the high phase data from consideration. The next thing I'd like to look at is a side-by-side comparison showing the long-term patterns of both Rankine and Caddy. To me, these look quite good. We can see that both instruments agree on a trend of increasing densities towards noon. And especially in the equinoxes, we can see lower densities towards nighttime and during winter. Now, one conclusion we can draw from these plots that was not immediately obvious before is that Rankine radar has a smaller range of measurable density values. We can see in the winter here, during winter nights, that Caddy measures density values as low or lower than 1 × 10⁻11 electrons per cubic meter. Rankine does not measure that low. Caddy also measures higher electron densities than Rankine during the peaks. For a more quantitative analysis, we did a direct comparison of all of our measured data where Rankine and Caddy had measurements within 1 minute of each other. We split these up into our normal time sectors and drew lines of best fit for each one. This would allow us to determine a correlation directly between Rankine and Caddy, as well as figuring out a formula that would allow us to relate the two in a more direct sense. In all 4 time sectors, the correlations are at least okay. Night and dawn are much weaker. However, these time sectors also have many fewer data points than the day and dusk sectors. We can do a similar analysis for riser data. Now, riser had 2 different beam modes, 2 different modes of operation that we considered differently. One of them was just 1 beam, the other was data collected from 20 riser beams. I'm not going to get into the differences, but fortunately, the results are similar regardless. The agreement between riser and Rankine is rather good during the day and dusk sectors, but is much less promising during night and dawn sectors. Now, one thing to keep in mind is that the number of data points in these plots is about an order of magnitude less than the plots for Caddy. Sadly, at very low densities, especially during this nighttime sector here, we can see that there are still many points of Rankine densities that seem very high to the point where it even causes a negative correlation in one case. This means that blindly removing all of those high phase points was not a perfect solution. It definitely helped, we've seen that it definitely helped, but it was not perfect. Overall, we found that SuperDARN's measurements of electron density usually agree reasonably well with measurements made by more specialized instruments, in this case Caddy and riser. We found the best agreement in the afternoon and dusk time sectors when electron densities are typically higher. This method of electron density estimation is not very accurate when electron densities fall below approximately 10⁻11 electrons per cubic meter. This is largely due to the fact that at such low electron densities, Rankine radar at least, does not receive much backscatter. We believe that the quality of electron density estimates from SuperDARN could be improved by better elevation angle determination. We hope to perform a similar study using the Hokkaido radar in Japan, because like Rankine, this radar has an ionozone directly in its field of view, which would allow, again, for independent density measurements. I have also built a ray tracing program which allows me to test propagation conditions for different ionospheric profiles. This allows us to test how the range and elevation of SuperDARN echoes are interrelated with ionospheric densities over a wide range of situations. This has been a short presentation of my recent work. Thank you for your time, and if you have any questions, feel free to contact me at sju861 at usask.ca. It's there on the screen for you.